Hello, this is the third session of our training course. In this session, I'm going to talk about forced convection. As I said in the first session, a forced convection is a type of heat transfer in which fluids are forced to move in order to increase the heat transfer. This forcing can be done with a ceiling fan, a pump, suction device, or other. The simulation of this type of heat transfer has fewer points than the simulation of natural convection, and its convergence is better. But one of the most important and difficult challenges in this field is to obtain the heat transfer coefficient. In the table here, you can see a suggested range for various types of heat transfer mechanisms. Please note that the given intervals may not be correct for the case or simulations you are considering, and it is only a suggested interval for the heat transfer mechanisms. In this session, I have simulated a water flow in a U-bend pipe, and I thought how you can calculate the heat transfer coefficient, Nusselt number, friction factor, and pressure drop. This simulation is based on an article provided in the attachment. The geometry used by the article is a U-shaped tube with a length of 1600 mm and a diameter of 70 mm. Inside the tube, a series of plates with holes are considered, and the diameter of each of these holes is 13 mm, and the distance between these holes is 20 mm, and the distance between them is 16 mm in the transverse direction. If you are looking to get the Nusselt number, you must know that this number can be averaged or locally dependent on x. For both Nusselt, you need to get the heat transfer coefficient first. To get the heat transfer coefficient, you need bulk temperature. Q and T parameters in the formula are extracted from the simulation. In most cases, Fluent software doesn't report the heat transfer coefficient correctly, and you have to extract this coefficient manually. Bulk temperature itself is mentioned in many articles on how to get it. Basically, when you are reporting the local Nusselt, you face more complications, but it usually has a higher analytical value than the average Nusselt. In this simulation, we have explained how to obtain Nusselt in average form. In heat transfer simulations, pressure drop and friction factor are calculated. You need to calculate the pressure drop first, and other parameters in the friction factor formula are fixed. If you used outlet pressure or pressure outlet, for your outlet boundary in your simulation, your pressure drop is just the average value of the pressure at the inlet boundary. Because you set your output pressure equal to 1 atmosphere, the software reports the output pressure as 0. But you may have used the outflow boundary condition, and at this time, you should read the pressure at the exit boundary and the inlet boundary and then consider their difference. Open the ANSYS Fluent software. At first, you must read the mesh. We consider three main assumptions in the simulation. First, we have chosen the pressure-based solver due to the incompressibility. Second, the simulation has been done as steady. And third, the gravity effect is neglected. In the model section, in the first step, activate the energy equation so that the software can calculate temperature changes. In the next step, set the viscous model to laminar because the incoming velocity is low, so that the flow regime in this simulation is laminar. In this step, you must define the water liquid as the material for the simulation. Click on the Create and Edit. Here, click on the Fluent database, select the water liquid under the list, click on the copy, and then close this dialog box. Now in the cell zone condition, click on the Edit, and then here choose the water liquid as the material. To set the boundary conditions, at first set the velocity inlet boundary for the inlet boundary, and then enter the velocity magnitude has been defined in the project description here, and click on the apply. Then in this section enter the inlet temperature and then click on the apply. Set the pressure outlet for the outlet boundary. There is no need to set anything here. Click on the apply. For heated wall, set the boundary type to wall, and then in its dialog box, the thermal tab, enter the heat flux has been defined in a project description, and then click on the apply. Now click on the make polyhedral to convert the mesh to polyhedral mesh. Note that this mesh reduces the size of your computing grid and at the same time has a higher quality. As can be seen, I have used the Presto discretization for the pressure and second order of wind for the momentum discretization and energy discretization. For discretization, for the pressure, you should use Presto, and for the momentum and energy equation, you should use the second order of wind discretization because this method provides more accuracy. Here, in the residual dialog box, disable all these options, otherwise, when the remaining equations reach these values, the software assumes that your solution has converged and stops the solution. Here, select the hybrid initialization and then click on the initialize to get the initial value to the center of all cells. And here in the run calculation, set the number of iterations and then click on the calculate. Once the solution is complete, in order to know if the solution has converged or not, you need to see if conservation of momentum is satisfied. For this, you must check that the difference between the flow rate of the inlet boundary and the outlet boundary is 0. As can be seen here, the continuity equation is satisfied. In the next step, you have to check whether the energy conservation equation is satisfied or not. Due to the fact that we have applied heat flux on the wall, the same amount of heat must be removed from the system. In fact, the heat of the whole system must be 0. In the last step, you must write case and data. Click on the right under the file menu, case and data, set the path, and then click on the OK. Now I wanna explain to you how the coefficients I mentioned at the beginning of the sessions can be obtained. Set up a table in Excel according to what you see. We know some of these variables from the project description. velocity, temperature inlet, Q, heat flux on the wall, and diameter, to obtain the temperature on the outlet boundary. Under the report, click on the surface integral, and then under the report type, choose the phase average, and for the variable, select the temperature, choose the outlet boundary, and then click on the compute. You can see the temperature on the outlet boundary. Copy this, paste the temperature outlet here, and for the temperature on the heated wall, do the same, but choose the wall heated boundary in this dialog box. You can see the temperature on this boundary. Copy this value and paste here. The bulk temperature, according to the formula mentioned in the reference article, is the average of the outlet temperature and the inlet temperature. So calculate this value. Heat transfer coefficient, H, is equal to Q, heat flux, divided by temperature differences, difference between wall temperature and bulk temperature. Thermal expansion, K, is equal to 0.6 for the water liquid material, and Nusselt number is equal to H times D divided by K. Now I want to show you how you can obtain the pressure drop. Click on the surface integral, choose the area weighted average for the report type, select the pressure for the variable, select the inlet boundary and read the pressure on this boundary, enter the value here. Note that, as I said at the beginning of the chapter, when you use the outlet pressure boundary condition in the problem settings to get the pressure drop, it is enough to read the inlet pressure because the software considers the pressure at your outlet boundary to be 0. Here, compute the L divided by D. L is the length of the U-bend. And now in this step, you can compute the friction factor using this formula. Follow my cursor point. Now I want to explain you how you can compute the local Nusselt number. At first, you must create some isosurfaces at different locations. As can be seen, I have created 6 isosurfaces, but you can create more or less. Here, from Create Isosurfaces, choose the mesh and choose the Z coordinate. And then create 6 isosurfaces for the fluid domain and also 6 isosurfaces for the wall heated. Follow my cursor point. Now in this step, you must read the bulk temperature from the surfaces you have created for fluid domain. Under the surface integral, choose the mass weighted average report type, select the temperature variable, and then select these surfaces and click on the compute. Then copy these values and paste them in an Excel file. In this step, you must read the wall temperature and the surfaces you have created for the heated wall. Choose the vertex average report type, select the temperature for the field variable, select these surfaces and then click on the compute. Copy these values and paste them in your Excel file. Here enter the Q. If you remember, we have this value from project description. And here, using this formula I have explained before, compute the age for each surface. And here, as a last step, compute the local Nusselt number using this formula for each surface. To benefit from MR-CFD services including simulation, consultation and training, visit our website www.mr-cfd.com and contact us via info@mr-cfd.com.